Today is the third day of this excellent series of talks by Ankur Moitra from MIT, and he's telling us about recent advances in high-dimensional learning. Today, supervised learning with mass art noise. So take it away, Ankur.
Great, thanks for coming, everyone. So just to put this in context of some of the other talks in this tutorial. So last time I talked about provably robust algorithms for parametric learning. So those were really in an unsupervised learning setting where you're positing some type of structure in your data. Things like, the uncorrupted data is Gaussian or has bounded moments that allow you to cope with corruptions to your data provably and in a computationally efficient manner so that you can still learn things like, what's the mean, what's the high dimensional covariance of your data. So today's talk will be about pushing back on some of those assumptions because, just like there's unsupervised learning, there's supervised learning where we're given a bunch of data along with labels. And, in supervised learning, sometimes you do and sometimes you don't want to make generative assumptions about where your examples come from. So that's what I'll be talking about today is, what can you do in supervised learning when you don't want to make strong distributional assumptions on your underlying data? Is there still some sense in which you can design provably robust learning algorithms? And here there'll be an interesting story about, the strength of different types of noise models. And the question will really be about finding the sweet spot that's both a rich model for noise and we can actually say something algorithmically interesting even in distribution independent settings. So let me start off by telling you about the classic framework for talking about supervised learning. This goes back to Les Valiant's famous paper back in 1984, in which he introduced the pack learning model. So here's how the pack learning model works. So we're given samples, which are X, Y pairs. You're thinking about X as being a high dimensional vector. And you think about the distribution on X as being arbitrary a lot of times. So there's some unknown arbitrary distribution on high dimensional vectors. And Y is a label that's +1 or -1. Now, the truth is you can think about richer labels than just +1 or -1. You can think about labels from some discrete or even continuous set. But let's keep it simple. So they'll just be +/-1 today. And the other assumption that you make is that there is some known hypothesis class, capital H, and there's some unknown hypothesis, little h, that lives in that class, and that all of your labels fit that hypothesis. So for each y that you observe, y is equal to h of x. So let's see what this framework looks like with some concrete examples. So one of the most important and fundamental classes of hypotheses is the class of all half spaces. So what you do is that there's an unknown vector W star and there's potentially an offset B. And now when you're given a high dimensional vector X, you take the inner product between W star and X and you add the offset B, and then you take the sign. So you output +1 if it's positive, -1 if it's negative. And you can figure out what to do if it's 0. You could just say you output +1 in that case. So geometrically, what your data looks like is it lives in some dimensional space. In this case, it's 2 dimensions. And then everything that's above the half space is labeled with a +1. And everything below your half space is labeled with a -1. Now, this is actually sometimes called the realizable case because you're making a very strong assumption, really, that there is an actual hypothesis within your family that perfectly fits your data. So ultimately, looking ahead in this talk, we'll be pushing back on that idea. What happens when there isn't a hypothesis that perfectly fits the data? But for now, let me tell you about the way that these problems are usually set up. So that was your generative model. You get to push a button and you observe X, Y pairs. And your goal is to estimate H approximately. So what do I mean by that? You can't really hope to learn the true hypothesis because even in the simple example, there are other linear separators that perfectly fit the data. So instead, what your goal is to estimate H approximately. You want to output another hypothesis, H hat, that has the property that it almost entirely agrees with the underlying hypothesis H. So this is called probably approximately correct learning. That's why it's called the pack model. So you allow yourself some failure probability delta. Maybe you just got really unlucky with the samples you're given. And you want your learning algorithm to be approximately correct in the sense that it outputs another hypothesis that agrees with most of the data that's coming out from your generative model. Okay, so there are tons of very powerful learning algorithms that are known in the context of pack learning. But now what I want to talk about is something that fits in with the last lecture I gave, which is, what happens if there's noise? Or to phrase it a different way is, what happens if you're faced with this very realistic possibility that there's no simple hypothesis like a linear separator that fits your data exactly. And now we're going to reach, some forking paths here because there are a few different ways that you can think about what this noise looks like. Let's start off with the easiest model for noise, the easiest one to cope with. So one thing that could happen is that each label could be flipped independently with some fixed probability, let's say a third. Now this is called random classification noise. And if I did flip the labels randomly and independently with some probability, let's say a third, I might get some collection of data that looks like this. Now there's a problem, which is that my class of hypotheses is the set of linear separators, the set of half spaces, but there is no half space that perfectly fits the data. At best, there's a half space that agrees quite well with the data. Now, it turns out that in random classification noise models, there actually are powerful learning algorithms. One of the seminal works in this area is the work of Blum et al. Back in '98. And some of the intuition, which we'll get into a bit later because it's going to come up in other guises in our analysis, is that there are a lot of iterative algorithms in standard pack learning, things like the perceptron algorithm. And there's a sense in which a lot of those iterative algorithms, like perceptron, that make some kind of progress with each step when they haven't reached a good hypothesis, well, if your noise really were independent and random, you would still have some nice progress in expectation where you're converging to the true half space that you wanted to learn. So that's some of the intuition, and all it is intuition for now. But what happens if we go to the other end of the spectrum? Because the truth is that assuming that the noise is independent and homogeneous across your domain is actually a really strong assumption that sometimes is just not really a realistic thing to do. So at the very other end of the spectrum is what's called agnostic learning. So that was like what I talked about last time, because last time when I talked about unsupervised learning problems, like learning a high-dimensional Gaussian, it was in an agnostic model because I made no assumptions on how the adversary was corrupting the data. He just had a finite budget, epsilon fraction of the data that he was allowed to corrupt. Same thing happens here, is that there's no assumption about the structure of the noise. Instead, what you want to do is that if the way that the adversary has added noise still has the property that there's a half space that agrees with the data quite well, you want to find one that has approximately the best agreement in the class. So if for some reason the way that the adversary added noise to your data preserved the fact that there was a half space that 99% agrees with your data, then you want to find a half space that agrees with, let's say, 98% of your data. That's agnostic learning. And again, it's called agnostic because you're not trying to make a religious assumption that there is a hypothesis that perfectly fits your data, or that the noise is independent like it is in the random classification noise model. Now, unfortunately, there's a problem, which is that agnostic learning and supervised learning problems is generally pretty darn hard. So we basically only know results that make some kind of distributional assumption on their inputs. So, there's a beautiful classic work of Kalai, Clivens, Mansour, and Servedio, and some improvements that were really powerful due to Awasthi, Balkan, and Long that showed that there's a polynomial time algorithm for agnostically learning half spaces when X is Gaussian. Actually, the difference between these results is that your goal is to try and get a half space that agrees up to accuracy opt plus epsilon, where opt is the best agreement. And Kalai et al. Gave an algorithm that ran in time d to the polyen epsilon, and then Awasthi et al., in the specific case of X being Gaussian, were able to improve it to a polyen 1 over epsilon times polyen d time algorithm. Now, the trouble is that this generally is what you have to do in this space, is that when you're trying to do agnostic learning, well, if you don't make any distributional assumptions, not only do we not know any algorithms out there, generally speaking, it's also true that there are hardness and there are lower bound results. So one recent lower bound of Danieli shows distribution independent lower bounds for agnostically learning half spaces. In fact, it's even a little bit worse because in his setup, there is the promise that there's a half space that agrees with 99% of your data, but it's hard computationally to find a half space that agrees with 51% of your data. So that's weak agnostic learning. So the main focus of this talk will be, are there challenging noise models where we can learn without making distributional assumptions on X? So I talked about two ends of the spectrum. One was the purely random noise model, and the other was one where we made no assumptions about the noise whatsoever, the agnostic model. But there are things that fit in between them that potentially fit the bill of being challenging noise models and yet allowing provable algorithms to work. So in this talk, the main thing that we'll be interested in is a model that I quite like. It's called the Massart noise model, in which here's the way that it works is that you think about each point X, that's one of your examples. It's going to have its label flipped independently with some probability eta of X. Now this probability eta of X is upper bounded by some eta. That's an upper bound of the noise rate across the entire domain. So you can think about eta as being a third. Now, the point is that the noise is still independent across the different points X, but it no longer has the property that it's homogeneous. So it can actually vary over different parts of the domain. So there's one interpretation of the Massart noise model that'll help you wrap your head around it. And then I'll give you an alternative interpretation that I'm very partial to. That's not quite the same thing, but it's morally the same thing. So you can think about it this way, as imagine that you started off with your random classification noise model, where you flip each label independently with probability eta. So you flip every label with probability a third. But now what you allow an adversary to do is he's allowed to unflip the label, to actually make it the correct label if he so wants. It turns out that many algorithms, like the Blum et al. Algorithm that work in the random classification noise model, they're actually quite brittle in the sense that when an adversary is allowed to undo some of the noise, their guarantees completely break down. So that's one of the surprising things. And that's why the goal is to find something that hits the sweet spot of being a flexible noise model while still permitting efficient algorithms. There's another interpretation that I really like. I wrote here sort of because it's actually not literally the same thing. But it turns out that all of the algorithms that I'll be describing that work in the Massart noise model will also work in this interpretation as well. So instead, what you can think about is you can think about the adversary as being allowed to adversarially control the labels in your data. The catch is that it's a random fraction of your data. So instead, what happens is that there's a random eta fraction of your data where the adversary is now allowed to control whether the label is +1 or -1. And the main question I'll be interested in is, are there distribution independent algorithms for learning with Massart noise? So now let me tell you about some recent results in distribution independent Massart learning. So there's a beautiful paper of Diakonikolas, Gouliakis, and Tamzos, which showed that there's a polynomial time algorithm for improperly learning half spaces under Massart noise. So, and they get error eta plus epsilon, where remember, eta is the upper bound on the flip probability that the adversary is allowed on each one of the data points. Now, their algorithm is actually quite complicated in the sense that it outputs something that's not a half space. Instead, what it outputs is something which partitions the entire domain into a polynomial number of regions. And there's potentially a different half space on each one of these regions. So that's the sense in which it's improper, is because it's not outputting an actual hypothesis, but something that's a much more complicated description of the classifier that you're using. And one of the natural questions you can ask is there a proper learning algorithm? So is there an algorithm for properly learning half spaces under Massart noise? Now, there's also another limitation of this, which is that all of the classic results in agnostic learning that worked for distribution-dependent setups, like having X being Gaussian or log concave, they all got error opt plus epsilon, where opt was the optimal agreement of anything in your class. So this guarantee only gives you an error guarantee of eta plus epsilon, where eta is the upper bound on the error probability that the adversary has added. So in principle, you could hope for a better error guarantee because maybe it's possible to compete with the best agreement among all half spaces within your class. So in some very recent work, which I'll delve into, so we gave a polynomial time algorithm for properly learning half spaces under Massart noise up to the same error eta plus epsilon. And what's kind of cool is that, the earlier paper of Diakonikoulis et al. Actually gave a no-go theorem for certain types of frameworks for learning, but we're actually going to give a general framework for learning under Massart noise that's going to be, it'll give you a good conceptual understanding, I think, of, how exactly you can cope with things like Massart noise. I should mention that this framework was independently discovered by Diakonikoulis, Kontonis, Tsamos, and Zarifis in a paper which handled distribution-dependent learning under Sibikov noise, which I won't get into. But one of the cool upshots of this general framework that I'm going to give you in this talk is that it also works for much richer families of hypotheses. So there are things you can do that are pretty interesting that are beyond half spaces that you can still do under Massart noise. Like there's something called a generalized linear model that we actually saw in Lenka's talk just about an hour ago. And what a generalized linear model is that there's an unknown vector W star. And for each data point X, we take the inner product between W star and X and we add the offset B. So same setup as a half space. But now we apply some function sigma that's called the link function. And the constraints that we impose on this link function are that it's monotone in Lipschitz. In particular, this includes things like noisy logistic regression when you plug in sigma, being a sigmoidal function, as a special case. So these are all things that you can do in supervised learning without distributional assumptions on X, actually under rich models of noise like the Massart noise model. Now, I'll just tell you a little bit more about the landscape of Massart noise and what's known. Because, and I won't get too much into this in the talk, but it actually turns out that there are some pretty surprising connections between learning with Massart noise and something called evolvability that Les Valiant introduced a few years ago. And one of the things that we showed was that lower bounds for evolvability turn out to imply lower bounds for learning under Massart noise. So one of the remaining questions which I posed is whether you can compete with the optimal agreement. It turns out that you can prove lower bounds in a natural framework for algorithms called statistical query lower bounds, that there's no polynomial time algorithm for learning under Massart noise up to error opt plus epsilon with a polynomial number of samples in runtime. And actually, this connection goes the other direction, that you can actually use algorithms in evolvability to give new distribution. You can actually get new distribution dependent evolutionary algorithms that are resilient to drift. Again, I won't get into that. All right, so I'm going to take a step back and tell you a little bit about how to think about learning with different kinds of noise models, because I really have to start from the basics about how you learn without noise and what kinds of convex surrogates are tailored to work with different kinds of noise models, even things like random classification noise. So I'm really going to present a different way of thinking about some of the earlier results. And that'll be the way we pedagogically build up towards being able to tolerate Massart noise and design some sort of general framework for thinking about algorithm design in this space. So let's start from the basics, right? So in pack learning, our goal is to get low error in terms of something called the 0-1 loss, right? So we can think about outputting some hypothesis W, and just for simplicity, I'm going to assume that there's no offset B. It's, you can do that actually without loss of generality in these setups. But if I think about my hypothesis W, so that the hypothesis that it defines is I take my vector X, my example, I take its inner product with W, and I take the sign of that. That spits out a +1 or -1. And I want to know how often that agrees with the true label Y that I see. This is the 0-1 loss because either you get 0 loss because you got the right label, or you get a loss of 1 because you got the wrong label. Now you can think about this a few different ways. This will be a convenient way to think about it is in terms of indicator functions. So if I take W transpose times X and then I multiply it by -Y, and I take the indicator function of whether that is non-negative or not. That's actually the same thing as the 0-1 loss, because remember what I want is I want the sign of the inner product between W and X to agree with Y. And if it did, then the product of those two would be positive, and then I take the extra minus sign outside and it would be negative. So this loss would pick up a 0 when I use the indicator function. And if I got the label wrong, I would pick up a 1. So this is how you can think about the 0, 1 loss through indicator functions. And now we can visualize what's happening because we take all of our data, which are really XY pairs, and what we plot in 1D is we take the inner product of W and X and we multiply by minus Y. And all of our examples land somewhere along the line when I apply this function. And this indicator function just looks like the step function. And wherever the example lands, that's what we pay. If it lands on the positive side, then we pay 1 for the loss. And if it lands on the negative side, it means that it's a correctly labeled example and we pay 0 in our 0, 1 loss. So now what's the main difficulty in classic supervised learning? We always want to learn in the 0, 1 loss, or almost always. But the trouble is that this step function is non-convex as a function of W. It's very clear from the way that I've drawn it. It's non-convex when you think about its dependence on this underlying vector W. So what's the standard thing that you do in computational learning theory is you define a convex relaxation. So this is a little bit different than, if you're from approximation algorithms, the sense in which you use convex relaxations is really they're called convex surrogates because you want to create some other convex function that behaves almost the same as the loss that you really want to minimize. So this is what leads to what's called the ReLU loss. So it looks almost the same as that description of the 0, 1 loss that I gave you earlier, that version with the indicator function. The only difference is that I multiply by the magnitude of the inner product between W and X. So that's the ReLU loss, and we can do the same thing as before. We plot all of our examples. We apply this function where we map them to minus Y times the inner product of W and X, and they land somewhere along this real line. And now what does the ReLU loss pay? Well, anytime it's negative, that indicator function is turned off, so you pay nothing. But the key point is that when it's positive, what you pay isn't the same thing. It's not always this fixed value 1. Instead, it's just a line of slope 1. Because as you get this magnitude more larger and larger, that's sort of like, you're really wrong in what you predicted. You thought that the inner product would be, something very large, but you got the sign wrong. So you pay something that's related to the magnitude of that. So now the upshot of the ReLU loss is twofold. First, the ReLU loss is convex now as a function of W. So I can actually just run an off-the-shelf solver like gradient descent for actually minimizing this convex function. That's how you derive things like the perceptron algorithm. That's where these iterative algorithms come from, is they actually come from convex surrogates. But the other thing is that actually I claim achieving 0 loss on the ReLU loss function is equivalent to fitting the examples perfectly, right? Because if it's possible to achieve 0 error in the 0, 1 loss, than it is in the ReLU loss too, because they agree perfectly on the left-hand side of the x-axis. And the only difference is that when you don't perfectly agree, the ReLU loss and the 0, 1 loss differ in how large your loss is, right? So now let's explore this issue and come back to some of the questions that I started off with. What happens when we add noise? So we no longer are in this realizable case where there is a half space that perfectly agrees with our data. Or equivalently, we're no longer in a setting where the minimum of the ReLU loss really is 0, because maybe there's no half space that perfectly fits our data according to either the 0, 1 loss or the ReLU loss. Now, if you think about it, what ends up happening, let's imagine that these are my pre-noise data points. So, beforehand, I have the correct hypothesis and it perfectly fits my data. But now what happens if I add random classification noise? I might do something like take one of the extreme examples and flip it all the way to the other side. So what's the problem with this is that the ReLU loss is really large now. It's way, way, way larger than the 0, 1 loss. So it's not representative of how many examples you're getting wrong. Because when the ReLU loss is large, it could be that there's just a single example that you've gotten extremely wrong. And alternatively, when the ReLU loss is small, it doesn't guarantee you have small 0, 1 loss because you could have tons of examples you get wrong. They're just very close to the decision boundary, right? So you could, just to summarize, you could incur a huge loss for a single mistake or incur a tiny loss if there are many mistakes as long as they're close to this y-axis. So just minimizing the ReLU loss, even in the case of having random classification noise, does not work. And that's part of behind what this Blum et al. Paper had to do. Now, it turns out that the Blum et al. Paper had a very complicated hypothesis that it learned because, much like the Diakonikoulis et al. Paper, it partitioned space into a bunch of different regions. Now, afterwards, there were a lot of simpler versions of it. One particularly nice paper was due to Adam Kalai, which showed that one way you can think about how to solve the problem in the case of random classification noise is just to change your surrogate. So instead of using the ReLU loss function, you use something that's called the leaky ReLU. Now, it's pretty simple. I think the hardest thing about the leaky ReLU is, what the word leaky has to do with it. But here's what it looks like pictorially. So it ends up having a slight slope, and it's off. That slope is slightly off from what the standard ReLU was. So what you do is this loss function looks basically the same like the leaky ReLU. You still have this indicator function. You still have this absolute value of the inner product term. But the difference is that there's a parameter lambda and you subtract it from the indicator function. So now if this indicator function were off, meaning that you actually got the label of the example correct when you use W as your hypothesis, instead of getting no loss, you actually get a negative loss. You get a slight gain. And in fact, you get an even larger gain if you're further and further from the decision boundary. So now what's the intuition for why this works in terms of the random classification noise model is that if you had an example that's far from the decision boundary, well, there's some chance that you get it right, that the noise, isn't added to that example, and then you incur a pretty positive gain because it's far from the decision boundary. If you choose lambda in the right way, that's actually perfectly offset by the big loss that you incur when it flips over the decision boundary. So the way that this works is that if there's some eta flip probability, there is a way to set this parameter in the leaky ReLU so that actually minimizing the leaky ReLU loss works for the random classification noise model. And that's the modern proof of how you get the Blum et al. Results, how you get algorithms that work with random noise. So now let's make things harder on ourselves because random noise isn't all there is. That's actually a very, very strong assumption. So what I want to do is I want to introduce you to a new way to think about how to design provably robust algorithms, specifically in the context of supervised learning. And we're going to do it through a two-player zero-sum game. That's going to be our framework for, what it means to learn and what it means to find, some region in space where we're doing poorly and we haven't yet reached a good hypothesis. So let me start from a two-player game that's not actually going to work, but it's the conceptually right place to start. So I'm going to create a very, very complicated two-player game. So what I do is there'll be two players. One player, the min player, is looking for a direction W. Remember that the direction W represents the hypothesis we want to learn. That's why we take the inner product between W and X and we multiply by minus Y, and we plug that all into the leaky ReLU. But now something kind of funny is going to happen is that we're not merely interested in the leaky ReLU loss. We're going to create a max player who is allowed to reweight the distribution. So he's allowed to create an arbitrary distribution C on space of arbitrary complexity. And then you look at the expectation of C of X times the leaky ReLU loss. So that's the intuition, is that the max player is allowed to reweight the distribution on examples to focus on some particular region in space where we're doing poorly. So the idea is that if you think about this Massart noise model, while the true hypothesis W is not only good in terms of 0-1 loss, but it also has the property that even if you restrict to any part of space, it still does well. And that's because the errors that the adversary has added, are randomly scattered over space. Now, they might not be entirely random because remember the second interpretation of the Massart noise model was that a random eta fraction of the data is where the adversary chooses where to add the corruptions, whether to make the label +1 or -1. But the key point is that it's somewhat homogeneous over space where those corruptions could be, at least in principle. So the intuition is that this max player is going to choose some distribution that hones in on the part where your current hypothesis is doing really poorly. So, the intuition now, just to sort of phrase it a different way, is that while you might do well overall according to the leaky ReLU because the adversary has added less overall noise, this max player can now always restrict you to where you're doing poorly, and that can force you to try and find a better hypothesis in terms of agreement with the data. Now, there's a simple claim that I'm not going to prove because this isn't really the zero-sum game I want to work with. What I claim is that if we could reach a minimax optimal solution for this two-player zero-sum game, then the optimal solution for the min player would actually be the true unknown direction W star. So this is the sense in which the zero-sum game is at least a reasonable thing to do. But there's another sense in which it's a very ill-posed way of thinking about things. Because let's think about what's going on inside the zero-sum game. So first of all, optimizing over the max player strategies is computationally hard because we're optimizing over all distributions over all of space. In fact, it's also statistically hard because I would just have to take an infinite number of examples to really evaluate what this expectation is. So this zero-sum game, doesn't really work for us because it's just statistically and computationally unwieldy. So the miraculous thing is that there's going to be a new version of the game that will work. Instead of the max player is choosing an arbitrary distribution over all of space, he's only going to be allowed to reweight the distribution in some very specialized ways. So imagine that the min player chooses some hypothesis W. And again, we have this leaky ReLU loss that we look at in expectation. But now what the adversary is going to do is he's only allowed to restrict the distribution to some slab along W. So you take your data and you project it along W, the current hypothesis for the min player, and you restrict the distribution to the slab of all points, which land in between -R and +R. So now all of a sudden, the max player is actually computationally efficient because once the min player chooses the W, this is just a single one-dimensional line search to find his best response. It's also statistically efficient. What's not at all obvious is the thing which really is the main part to show is that this zero-sum game is still good enough. Any approximate equilibrium actually does correspond to a hypothesis W that has low error. So that's the miraculous part. And this is really a general framework that you can try for other kinds of generalized linear models. And it's just a way to think about how to cope with Massart noise as you want to play a minimax game against someone else who's allowed to pick out parts of your distribution in a very specialized way and say, aha, you're doing poorly here, do better. All right, so let me tell you about some other classic things in computational learning theory to build up towards the analysis. The truth is the analysis is actually pretty darn simple. So I'm going to be able to give you the full analysis today. In fact, parts of it are going to borrow on the earlier work. So I'll explain how those things worked, at least some of the key lemmas from them. So first, we need this fundamental notion called the margin. Many of you will have probably heard it, but let me just define it anyways. So the margin is the smallest distance of any example from the decision boundary. So pictorially, what does it look like? Remember, when we have the 0-1 loss, we plot the examples according to where they fall in the real line. And the margin is just the width of this interval, how close any example is to the decision boundary, which corresponds to the case where, along the real line, you're looking at the 0 point. So the key lemma, we're only going to have 2 key lemmas, and that'll actually complete the proof of the thing, modulo 1 minor extra detail. And let me tell you the first key lemma. We can actually borrow it from some previous work. So key lemma number 1, due to Diacono-Collis et al., is that in the Massart noise model, let's say you choose your lambda parameter, which remember is the parameter in the leaky ReLU loss, and you choose it in such a way that it's at least as large as eta, the upper bound on the noise rate. And your distribution on X has some special property that it has margin at least gamma. Then what I claim is that if you plug in the true W star into your leaky ReLU loss, that it will have low loss. In fact, it'll have negative loss according to the leaky ReLU loss, where your upper bound depends on the margin. It depends on this parameter lemma in your leaky ReLU loss, and it depends on the error of the true W star. So this is the first key lemma. And this lemma is super short. I mean, the proof isn't even going to take up this full slide. It's just a matter of actually writing out the definition and remembering what the descriptions of the leaky ReLU loss are. So the first thing that I'm going to do is I'm going to write out the leaky ReLU loss using that expression that I did before in terms of the indicator function and this lambda parameter times the absolute value of the inner product between W star and X, right? The only trick is that what I'm going to do is I'm actually going to use subconditioning. So first, this first expectation is its expectation is over X, the draw from the domain. And this remaining probability is on the randomness of the noise. Let's work on that first interpretation where the adversary adds some noise eta of X that's independent across each one of the data points and is upper bounded by eta. So this is all it's using is the definition of the leaky ReLU loss and the notion of subconditioning. So now what do we do? Well, this probability that the true W star agrees with the label that we observed is equal to eta of X, which is upper bounded by eta, which itself is less than lambda by assumption. So in fact, when we plug in this, what this means is that this entire term is negative. So instead we can plug in the lower bound on the margin, and that's going to give us an upper bound on the leaky ReLU loss. That's it. That's the first key lemma. And we only have one more key lemma to go until we're done with the analysis. So abstracting what this key lemma tells us, it tells us that the true direction W star achieves small loss. That's good. That's an important property in even the setup of our zero-sum game. And one point I want to point out is just a conceptual point in this, right? Is that, what's also true is that imagine that we take our problem and we restrict the domain some way. We restrict to a slab, we restrict in some other way. This analysis would still carry over because we would just have a different distribution on X. So this is the part of the Massart noise model that we're really exploiting, is that this type of proof and this type of analysis even works under restriction. And just to emphasize, this is not at all true for agnostic learning. Because in agnostic learning, where the adversary is allowed to add an arbitrary eta fraction of corruptions and distribute them over space however he sees fit, he can concentrate them in some part of the domain. And then when you restrict a part of the domain, that part of the domain might have a much worse error rate than the rest of the domain. So this is one conceptual difference between the Massart noise model and the agnostic model. And we can see where exactly it comes out in the analysis, even in such a simple key lemma as this. So I'm half done because I only have one more key lemma left to go. So let me tell you the key lemma that we're going to need to complete, this analysis of why reaching an equilibrium in this game is good enough to solve the learning problem. And this is actually a simplified version of the lemma that's in our paper. What I claim is the following. If you're in the Massart noise model, suppose the error of your current hypothesis W, and by error I mean the 0-1 loss, is larger than lambda, where again, lambda is the parameter of your leaky ReLU loss. Then what I claim is that there is some slab. Remember, a slab is defined by direction W and some threshold R, where you look at points between -R and R. There is some slab where the leaky ReLU loss restricted to just the portion of the distribution that falls within that slab is large. So we know that the true W star has negative loss, and yet by virtue of the fact that W has large error, this loss on some bad slab is actually too large. It's not only not negative, it's actually positive, potentially. So what does this mean if we can prove this key lemma? Well, what it means is that if the current direction W does not get small enough error, then the max player can do well in the game because he can find a slab along the current direction W in which the leaky ReLU loss restricted to that slab is larger than it should be. And so in particular, the converse to this is that if we're doing well with respect to the min player, that's actually equivalent to achieving small error. That's the thing that we actually care about for our learning problem. So let's prove this key lemma. This will be, the only remaining proof I have left in this talk, but then I'll talk about some conceptual things about this work. So, suppose for the sake of contradiction that there is no slab where the leaky ReLU loss is large. There is no R, right? So let's literally translate what that statement means. That means for every R, well, when I plug in the definition of what the leaky ReLU loss is, looks like the same thing. It's got this indicator function minus lambda times this absolute value term. And then I have this indicator function of whether or not the point falls into the slab, right? And so for the sake of contradiction, if there's no slab where the loss is large, then for every R, this expectation is strictly negative, okay? And this is just the loss times the indicator function of the slab. Nothing much is going on here. Now we're just going to use a really simple identity. Well, for any x that's positive, that's the same thing as integrating the indicator function of whether y is less than x along from y from 0 to infinity. That's a pretty simple integral identity. But the key point is that this identity is going to allow us to absorb this absolute value term inside this indicator by adding a new variable, not y, but the variable s. And the result is that we integrate over s. So if we absorb that inside, we get this identity. And here again, we've done the same subconditioning trick where the first expectation is over x, and the remaining probability is over the noise that happens that decides what the actual label y is. Now we're basically done because that integral being strictly negative means that there's some value of s for which the thing inside the integral is -2. So for any r, there's some s of r where that term inside the integral is strictly negative. And now we're actually done because we can just rearrange. We pull the lambda on the other side. This indicator function, well, if we divide by the probability being in the slab, we get a conditional probability of, the probability we get the sign wrong, conditioned on actually being in the slab. And we know that lambda is a strict upper bound for it. And that's actually going to give us a contradiction because now we have a slab where our hypothesis W is actually doing well. And we can chain together a bunch of these regions. We start with R, we find another S of R, and that finds us some slab where we're doing pretty well in that slab. And that gives us a new R that we find a new S of R, and that gives us another slab, which we're doing pretty well. And if we chain together all of these regions disjointly, then we get an upper bound on our error that we really have found a good W that achieves good 0-1 loss. And that completes the proof by contradiction. That's it. So that was the most technical part of the proof. But my point was that it's actually a very simple analysis. And now let's put this all together into an actual algorithm, right? Because what we've said so far is that we have a 2-player zero-sum game where it suffices to reach a good equilibrium in order to solve the learning problem that we care about, even in a rich model of noise like the Massart noise. So now how do we actually find a good equilibrium? Well, probably many of you have seen these kinds of things before. All we do is we do it iteratively. We start with some guess for the min player randomly. Let's say we choose W randomly in the unit ball, doesn't really matter. And then what we're going to do is the max player is going to try and do well in response. So the max player is going to try and find a slab, let's call this slab defined by R star, that maximizes the leaky ReLU loss on that slab. Now, if the best the max player can do really isn't all that well, because the best slab he found only has loss at most epsilon, then what our key lemmas tell us is that it suffices just to return W, because the max player can't do well. And the only way that that's true is if the W that we found right now really does have small error. So we've solved our learning problem. What happens if the max player does well? He finds a slab in which the loss is actually quite large. Well, we want to learn from that loss. In fact, what we do is we're going to exploit the convexity of the loss function because we just take its gradient and we take a step opposite to the gradient and project back into the unit ball because we care about a unit vector W. Now, the real version, you have to care about a lot of details like sample complexity bounds using the empirical loss and what have you. Doesn't really matter. Those things do work out. But the key point in why this type of thing converges in a small number of steps is that the leaky ReLU loss, remember, is convex as a function of W. So what does it mean when the max player has found an R star where our leaky relu loss on that slab is much larger than the optimal thing, W star. Well, when this left-hand side is actually quite large, then the fact that the leaky relu loss is convex, it means that there's a lower bound on the inner product between the negative of the gradient and the direction that points from W to W star. And so when we have a large left-hand side, that means that somehow when we're playing the strategy W against something that looks like the gradient, we're doing a lot worse than we could have done in hindsight if we had just played W star. So this is actually what's called online convex optimization, which the framework in online convex optimization is that there's some convex body. In our case, it's the unit ball, because you were interested in finding a W that's in the unit ball. And each time step, the adversary plays a convex function. In our case, it's a very simple convex function because it's the gradient. And what we incur is we incur the evaluation of the function at the point that we play. And the goal is to compete with the best point in hindsight. So putting it all together, every time that this iterative game goes on and the W that we play doesn't work well in when the max player responds to us, it means we're doing much worse than we could have. And yet online gradient descent and projected versions of it are known to achieve low regret. So this actually can't happen for too many time steps. And that's actually how you complete the analysis. So now in the few minutes that are left, what I want to do is I want to introduce maybe a crazier idea. I'm not going to say that this necessarily makes sense, but it's definitely something that's worth exploring because it's very intriguing. So, maybe I want to address the question, when are some noise models more reasonable than others? Massart noise certainly sounds hard to get provable learning algorithms that work with it. But, what kind of setting is it really helpful to try and work with Massart noise rates that vary across the domain? And let me show you an experiment that's motivated by questions about fairness. So when is this noise model of Massart noise useful? Well, let me tell you about an experiment we did. So we took this UCI adults data set, and if you don't know what this is, let me explain. So there's about 50K individuals in it. Now, each individual is defined by a vector of attributes. There are like 14 attributes, things like marital status, education level, and what have you. And the goal is to take this vector of attributes for each one of the individuals and predict whether their yearly income is above or below 50K. So it's a pretty simple prediction problem. And we did something a little bit weird here, which is that, there are many different types of demographic groups within this data set. So what we did was we added random noise outside a target group. So we added noise to everyone else except for some target group. And we ran off-the-shelf algorithms whose goal is to get an accurate classifier. And something kind of wild happened. But first, let me motivate it. So, one reason why you could think about this noise rate being different across different demographic groups is actually there are tons of empirical studies showing that this indeed is the case. When you do things like you send out surveys in the social sciences, it's well known that how accurate the answers you get vary across different demographic groups. It could have to do with, what types of language they're fluent in. It could have to do with whether they trust the system which the surveys are coming from. Will it actually be, ultimately that data be used for something that helps them, or will it harm them? Sometimes people refuse to answer surveys because they've had such a set of negative experiences with, the government and what have you. And so what we did was we took the setup where we added noise to everything except for the target group. And we took off-the-shelf algorithms that tried to maximize the overall accuracy, and we measured how those algorithms did in terms of accuracy on that target group where we hadn't added the noise. Now, something kind of wild happens if you take, for example, like the target group of African Americans. Then what you can do is you can add varying noise rates outside to everyone else who's not in this demographic group. And you can take a bunch of off-the-shelf algorithms like random forest, logistic regression, and algorithms that learn under random classification noise, and you can see how well they do at the prediction problem overall over the entire group of samples. And you can see that they all achieve about the same overall accuracy for different noise rates. but some of them do catastrophically worse on small demographic groups within the data. So in fact, when you add 20% noise to the entire population outside of this target group, a bunch of these off-the-shelf things like logistic regression predict that almost no African Americans from the group have income above 50K. This is pretty horrible. In fact, it's horrible across a bunch of different demographic groups. When you do it with female, same thing happens. And when you do it with immigrants, same kinds of things happen, although the degree of this effect varies across these different demographic groups. But what's nice is that our algorithms, which are designed to work with noise rates that vary across the domain or across different demographic groups, they achieve the same overall accuracy while not having this catastrophically bad performance on different target demographics. So I'll say that random forest does quite well too. Now, random forest, it's an interesting open question to try and analyze it in complicated noise models to understand why it's doing so well. But it does have this downside that it's actually much harder to interpret because it doesn't output something as simple as like a simple half space. But then again, what is and isn't interpretable is kind of in the eye of the beholder. So in summary, what we found from this experiment is that many natural algorithms that are designed to achieve good overall accuracy, what happens is when they're faced with varying noise rates across the domain, they tend to amplify biases in the data. This is something that I haven't seen studied too much, and in contrast, our algorithms, which have provable guarantees when the noise rates vary, these actually tend to do empirically much better, and they do so even without knowing the identity of these protected groups that you want to make sure are not disadvantaged. So let me take a step back and philosophize wildly about this. So within algorithmic fairness, I'm an outsider, but there's tons of really interesting stuff happening there. There are a lot of definitions like equalized odds and calibration that actually come from normative considerations and a lot of, philosophy literature at their core that posit, what you should ask of your classifiers. But, the truth is that often they're pretty difficult to achieve in a lot of settings. So I guess I'm asking a much more naive question, which is in a lot of settings, we might have some idea about what are the ways that, noise enters into our data and the way that it treats different subgroups differently. Now, can algorithms that are designed to cope with these rich noise models do something practically relevant vis-a-vis fairness? Can they actually do better? Does making your algorithm robust to richer noise models empirically do things that make it perform without these giant gaps in performance across different demographic groups? Maybe because it can tolerate heterogeneous noise. And for those of you who know these kinds of things, just to tie this back in, even with some of the things that I talked about last time, you might be wondering how all of this fits in with differential privacy. See, differential privacy algorithms are known to be robust, and they've even been used for fairness. But there's actually a difference in how these problems are set up in the context of learning theory and how they tend to be set up, within the context of privacy. So in the context of privacy, usually your notion of what it means for an algorithm to be differentially private or to be robust is that if you change a small number of examples, you shouldn't change the output of your classifier or statistical query too much. But here we're working at a very different end of the spectrum, which is not when a constant number of examples are corrupted, but when a constant fraction of examples are corrupted. And instead, we're making distributional assumptions on our input. So these are actually quite different in the sense that differential privacy is not trying to make distributional assumptions and tries to tolerate a very small number of changes in your data, a universal constant. Whereas a lot of these questions that I've been asking have been about, what can you do when you actually posit a little bit more structure in your data? Is there a sense in which you can actually tolerate some constant fraction of noise? So I'll stop there and, summarize what I hope you got out of it. So, there's a lot of interesting stuff that's been done in robust supervised learning. You can think about many different models like random classification noise, agnostic noise models. The trouble is that as much as we would like to do things in agnostic noise, generally it's hard to do it without distributional guarantees on the inputs. And what I was trying to make the case of is that there are interesting models that are compromises in between them, where you can have rich noise models and yet you can design provably robust and computationally efficient algorithms. So there's a ton of interesting stuff in the space to explore. I gave you some generalizations to generalized linear models, although I didn't show you how to prove them. And then I asked a wildly out there question, which is, all the stuff that people have been doing in robustness and unsupervised learning, robustness and supervised learning. It seems to me like, one of the stories that we can tell about noise relates a lot to fairness considerations. I wonder if any of these algorithms or even these algorithmic insights have anything to say. So I'd love to hear your inputs on that. So thanks for your attention. Just give me 1 second. I think my audio is dead.
Okay, thanks, Ankur, for another great talk. I guess there's a couple of questions that have popped up in the Q&A, so maybe we can start with those. And if you have a question that you want to ask live, raise your hand and one of the hosts will unmute you.
Hello, can you hear me? Hey, I'm sorry, I actually couldn't hear when you said that. Would you mind repeating it?
Oh, I just said let's start with the questions in the Q&A and
oh, sure. Yeah.
And yeah, okay.
Thanks, horrible talk. Okay, let's see. If the noise were actually from the logistic model, does your algorithm still work? That's a great question. So this is a pretty technical one. So let me do my best to explain it. So what's kind of funny is that this generalized linear model, remember that the setup for that was that there's sigma of W transpose times X. And actually it works in something called the probabilistic concept model, because sigma is actually, a value between -1 and 1. It's not a value of, necessarily of the two. So there's this thing called the probabilistic concept model of Kearns and Shapiro, in which what you assume is that there's a, that's the expectation of your label. So that's the setup even for the classic, generalized linear models. And a bunch of those things you can think about as subsuming random classification noise, because even if you had something like an actual, indicator function was your link function, then if you added random classification noise, you could actually fold that into changing the link function, because you would just move the expectation closer to 0. So a bunch of things where you assume something about where the noise model is actually simple, like it's random, or I think in your logistic setting, you can actually fold it into the link function, and you can just use Kalai's algorithms for learning under generalized linear models. That's also related to this other point that I made, that doing gradient descent on the leaky ReLU loss is the right way to think about how to learn under RCN. That was actually the output of one of Kalai's papers with Sastry, and then sort of further clarified in one of Kalai's later papers. And it's also tied to some earlier things in the machine learning literature, where they studied if you have a link function, what's the notion of a matching loss that has the property that anything that minimizes the matching loss is necessarily a minimizer for the loss that you care about. And proving things like it has no spurious local minima. So a bunch of this literature is sort of very convoluted. I can add a plug that I learned a bunch of this stuff, obviously through my students, but and they learned it through some of Varun Kanaday's excellent lecture notes that I think helped give a modern perspective on it. Mickey asks, what happens if there is some structure in the noise probabilities? For instance, the noise probabilities eta of X are a decreasing function of the distance from the decision boundary, but otherwise are arbitrary. Does this help? That is a really good question. I'm afraid I don't know much about it. What I would believe, I'm happy to be wrong if anyone knows anything else in the literature that works with those kinds of noise models. But just to add a little bit of background, at least what I think about, whether that would be a tractable model to work with or not. So at one end of the spectrum, you could make a parametric assumption here, because you could assume something about how eta of X depends on the distance from the decision boundary. Like maybe it's a function of the distance to the decision boundary. And that actually might be doable because, you know, a lot of those parametric models, you can actually cope with like some sort of structure about what your noise looks like. So I haven't seen anything, but it sounds like a pretty algorithmically tractable thing to try and study. But if you merely have a one-sided bound that the error probability is at most this function of the distance of the decision boundary, then it's really a non-parametric model for the noise. And those things tend to be really nasty to deal with. Something that is related is something called the Sibikov noise that doesn't encode anything about the geometry, but instead posits some structure about the distribution on what the eta of x's look like across your entire distribution. You can't have too many of them that are too close to a half. Could you summarize the different notions of robustness studied in learning theory? Okay, so this is going to be a tough one, but let me at least start by summarizing some of the notions of noise that I talked about so far in my 2 talks at least. So first, there were notions of noise in unsupervised learning models, and there was a whole cornucopia of what it means for an adversary to corrupt data, because there are different versions of the adversary depending on if they choose their corruptions obliviously, or if they're allowed to adapt, or if they're only allowed to add data. Those are insertion or injection models. And there are versions where they're allowed to delete, and those are called strong contamination models. That's more in the context of unsupervised learning. Sometimes you'll hear this called many different things. It'll be called the data poisoning attack, or it'll be called model misspecification in a bunch of settings. But even then, there are a bunch of richer things that I didn't talk about because, you know, what happens instead of the adversary as moving you to another distribution that's close in total variation distance, I could honestly choose any distance measure on probability distributions I wanted. So if you chose the Earth mover distance, that would be another way to set up robust unsupervised learning. I don't start off with a Gaussian, but I start off with something that's close in Earth mover to a Gaussian. You know, that's also a perfectly valid noise model. It actually turns out to be way easier than for the total variation version. And then I talked about supervised learning in this context. So, you know, here we only talked about corruptions on the labels. So there was the random classification noise where it's random. There was agnostic where it's completely arbitrary. And then there were mixed things in between where the adversary was allowed some adversarial control, but the points that he had within his control were randomly scattered. But even then, that's not the end of the story because there's another cool one where the adversary is allowed to tamper not just with the Y, but also with the X. And that's called the malicious noise model. And there's some really nice work, you know, of Awasti, Balkan, and Long on these types of things, which I encourage you to check out. This is probably not even an exhaustive list, but these are at least some popular ones that I know. Were the random forest results sensitive to any parameters such as number of trees, use of bagging? Actually, they weren't. We didn't try bagging, but the number of trees, they weren't that sensitive as far as I can remember. But one of the things is that these random forest results are not in extremely high dimensions. I mean, we're talking about 14 attributes. So, you know, an interesting question is, could you prove guarantees about how random forest works, especially under rich noise models like Massard or what have you? But you could also wonder, even experimentally, whether these things carry over to high dimensional settings. I don't think we really know the answer to that, but you know, random forests use a lot of distances in how they decide to make their decision boundary. And for a lot of high dimensional problems, that's where, you know, distances without learning something about the underlying structure of your data tend not to be very useful things to do. See, even if we go way back to my first talk, when I talked about learning mixtures of spherical Gaussians, then when you learn them, they can actually be incredibly overlapping. And what happens is that a sample from one Gaussian might actually very often look like it's closer to the center of the other Gaussian than it is to its own center. But it's only when you find the direction that connects the centers of the means that you find the right intrinsic distance to actually use to measure, you know, which points are close to which other ones. So it's quite possible to me that some of these random forest results empirically that it's good might go out the window in high dimensions because maybe they're not actually adapted to, you know, the right notions of distance in high dimensions because of things like concentration of measure phenomenon underneath it. There is Adam Cliven's, there is a paper by Bylander about learning half spaces with noise rates changing as you move the decision boundary. Okay, neat. I'll have to check this out. I've seen a citation of this, but I've never actually read it. Adam, do you happen to know if there are distributional assumptions on the x's, or I mean, is it a mixture of like distributional assumptions on x's and noise rates that vary geometrically, or can you do distribution independent and geometric noise?
I don't think there's an assumption on the distribution, but there may be sort of a strong assumption on how the noise changes as you move towards the decision boundary. I can't quite remember.
Okay, and I guess we would have to check it, but I've certainly seen a bunch of settings where it's a noise being parametric versus non-parametric in this way, like if it's monotone versus it is this particular monotone function, seems to really change things, especially when you talk about like, iterative algorithms making progress towards the correct thing, but I guess to be determined. I don't quite know. And I should also mention that there's been a whole bunch of other distribution-dependent agnostic learning results. So I only had time to tell you at least a couple of the highlights, like the KKMS paper and the ABL. But there are results when you talk about X is Gaussian, X is uniform on the hypercube, X is log concave. A lot of those distribution-dependent things, at least certainly the first wave of them, use polynomial approximation as one of their key pieces. So they're sort of using, the fact that you have Fourier analysis and orthogonal polynomials, but they use, some very clever L1 regression types of things to get agnostic guarantees. And there's a big difference is that when you get distribution-dependent agnostic learning results, you're shooting for something much stronger, which is I don't want eta plus epsilon agreement. I want opt plus epsilon agreement, which could conceivably be, much better, and often is actually.
Ankur, just a quick follow-up on the question that I asked about logistic regression. Can you hear me?
Yeah, I can.
Okay, awesome. So just a quick clarification here, and it actually ties back into what you were just saying about the metric itself. But if I just wanted to estimate the half space, or if I just wanted to estimate W star in this model, then the rates for estimation should be less sensitive to non-parametric noise. Is the intuition correct? Like I can still get root n consistent estimates of the parameter, even if I have non-parametric noise, right? I mean, in the prediction norm that you're considering, it could be much, much worse,
yeah,
conceivably.
Absolutely. Yeah, I agree. I don't know a citation for that, but that certainly seems very consistent with my intuition. One of the distinctions, just to sort of elaborate a bit more on that, because I would still have to think a bit about that particular noise model. But if you take the Blum et al. Result, back from 98, that actually doesn't just achieve low error. It does something better. Because, the best error you can achieve in terms of agreement with the Y's you observe is, eta, right? Because there really is eta noise that's added. But they actually do better because they converge to the W star. So what's true there is that, anything that actually does achieve small enough error, because the noise is actually random, will necessarily, get closer and closer to W star. So if you formulate these goals with certainly for random noise models and for structured noise models, there are fundamentally things that you can do in terms of what problem I can solve that you can't do in some of the other things where it's, impossible in some of the Massart-like noise models and stuff, I think.
So the actual parameter recovery is impossible in the Massart model, is what you just said?
Yeah, I think so. I have to double check.
Got it.
I remember some discussions about this, but that is the type of thing that these noise models might, cost you, is that sometimes you can actually solve a stronger problem like parameter recovery in the random things or in the structured noise.
Got it. Thank you.
And what is known about proper learning in the agnostic model with distributional assumptions? So, I'm likely going to have to tell you like a caricature of an answer, and then maybe I can defer to Clivens if he's still here. But one thing that I didn't talk about is, so this Daniele result, if I remember correctly. So first of all, it's awesome because it's a weak agnostic learning lower bound. It's hard to go from 99%, you know, as the promise, even to 51%. That sucks. And in fact, you know, it really does use the fact that it's a very tailor-made and kind of strange distribution because it comes from some random CSP assumptions. But it's also hardness, if I remember correctly, for improper agnostic learning. And there's a big difference that, you know, when you talk about hardness of proper agnostic learning, you can actually prove things, you know, based on NP hardness. And these are maybe some of the old Blum and Revest papers from way back when. But when you're talking about proving hardness of improper learning, that's a much trickier beast. There are reasons why you wouldn't expect it to be based on hardness, you know, NP hardness. And, you know, some of the really important work here is like the Cliven-Shersov paper that showed hardness, I think, in a distribution independent way. So, you know, for a very, you know, I mean, a particular distribution that comes out of crypto, but they showed hardness of improperly learning intersections of half spaces, for example. And, you know, there it was really based on some of these ideas about if you could solve the learning problem, regardless of what hypothesis you output, you know, because it's improper, you would then be able to break various lattice-based crypto schemes. Now, I don't know, so already in your question, when you have proper learning, you can do a lot stronger things here because, you know, even when you talk about distribution independent, you're in the realm of potentially basing things on NP hardness as opposed to basing it on crypto. But I don't know of very much for proper learning in agnostic model with distributional assumptions.
Yeah, so I mean, it's if you take a distributional assumption, like I think the Awasthi Balkan Long paper, I think it is proper. You'll get order opt plus epsilon. Now, if you want to do opt plus epsilon and it's Gaussian, being proper is open. It's still open. And Amit Danieli has this p-TAS for you know, getting close to opt plus epsilon under a distributional assumption, but that's also not proper.
Any more questions? All right, so if there's no more questions, thank you again, Ankur, and we'll see you all at the coffee break in the Gather
I'll
Town.
say one last thing that my next talk, it'll get even weirder. So we'll see, it'll be even more wild pontifications. So if you prefer fewer theorems and more wild pontifications, be ready. We're gonna go into physics.